one of the members of my program committee, Bill Shaddad, W9MXQ, is a longtime friend of tonight's speaker and offered to give a brief introduction of Carl Luetzelschwab K9LA. Bill, go ahead, please.
Okay, you did pretty good with the pronunciation, didn't you, Carl? I was impressed, okay?
Yeah, I'm impressed.
So I want to introduce tonight, and he's here with us on Zoom, Carl Luetzelschwab, K9LA. He comes to us tonight from his QTH in Fort Wayne, Indiana, and that's home for both Carl and his XYL Vicky, AE9YL. Carl and I have something in common with Fort Wayne, by the way. My mother's family is all from Fort Wayne, and some remain there to this day. Carl was first licensed in 1961. That means you're older than me, Carl. He graduated as a ham, I guess. He graduated as an electrical engineer from Purdue, and he was an RF design engineer for Motorola and Magnavox Raytheon. Carl's ham radio interests include contesting, DXing, antennas, propagation, CW traffic handling, and vintage radio equipment. Carl was, as many of you know, ARRL Central Division Vice Director from 2017 to 2020, and ARRL Central Division Director from 2021 to 2024. And as he likes to say, in post-retirement, Carl reports that he is now Chief Litter Box Scooper Outer for 9 cats. So with that, I present you with Carl, K9LA, who's going to speak on Propagation 101. And Carl, I will make you a co-host so you can share your screen.
Okay, thank you, Bill.
You're welcome.
I have to admit I enjoy reading Bill's vintage equipment columns in the newsletter. And I remember a lot of those radios and even have some of the ones he talks about. So that's good. Hello to Jean Ann tonight. Also Gary, W9XT. We usually get together and talk a little bit at the AHRO Superfest. Whatever. And we have 8 cats, not 9, but still that's okay.
I stand corrected.
Yeah, we about a little bit over 2 years ago, we adopted a litter of 7 kitties. So they keep the house pretty active. And admit we have an adult male also. He's finally gotten used to them. There are some sparring contests every once in a while, but not too much anymore. Okay, let me bring up my do the share screen here. Okay, great. So what I'm going to talk about is some basic stuff. That's why it's called Propagation 101. Mostly HF, 80 meters through 10 meters. I'll talk a little bit about 160, which is medium frequency, MF, and also 6 meters, which is our first VHF band. For those of you who are techs, of course, you have privileges on 10 meter sideband CW and digital, and you also have some CW allocations on some of the HF bands. So hopefully you can get on at least 10 meters and get on the HF CW. It's a great way to work quite a bit of DX. So let's get started here. Oh, shoot, that didn't work. Hey, that worked. Okay. Here's the agenda. We're going to talk about the sun, the atmosphere, and the ionosphere. That's just a basic introduction. Then we'll talk about solar cycles. We'll talk about fundamentals of HF propagation, and I'll give you some interesting details that will help you in your use of the HF bands. Talk about space weather. We can't avoid it, unfortunately. And then, of course, a very quick update on cycle 25 and how it's doing. So the sun, the atmosphere, and the ionosphere. Well, it all starts with the sun. It's because the sun emits electromagnetic radiation at many wavelengths, from very short wavelengths, which are gamma rays, X-rays, extreme ultraviolet, UV, to very long wavelengths, which are the radio wavelengths. The most intense radiation is at visible light wavelengths, 400 to 700 nanometers. You can see that in the plot there. And the important range of radiation for our amateur radio activities, HF activities, are the very short wavelengths. These are called ionizing wavelengths because their wavelength is short enough and the energy of a photon has enough energy to strip an electron from an atmospheric constituent like atomic oxygen, molecular oxygen, etc. And you can see in that graph where the ionizing wavelengths are way on the left. That's where the extreme ultraviolet and the X-rays are. Also, if you move to the right, you'll go through visible light, the infrared, and then there's the 10.7 centimeter solar flux. So that's a good indication that 10.7 centimeter solar flux has nothing to do with the ionization process. It's just a proxy for the extreme ultraviolet radiation, and it can be a good one at times. And of course, as we go further to right, we hit 10 meters and then 160, and then the AM broadcast bands and all that. So the sun is very helpful. It's what sends radiation towards Earth, and that results in the formation of the ionosphere. And this ionizing radiation creates regions, and the regions depend on the wavelength of the radiation and also the altitude and concentration of the neutral constituents in the atmosphere, the oxygen, nitrogen. And I guess I should mention that our atmosphere is about 78% nitrogen, 1% oxygen, or 21% oxygen, and 1% a bunch of other little trace elements. Now there's a picture of the ionosphere during the day on the right. There are 4 regions that we are concerned about: the D region, the E region, and the F region, which during the day can split into 2 different regions. We'll get to some summaries of the different regions on the next slide. At night, the D region, for all intents and purposes, goes away. And the 2 F regions, F1 and F2, combine into the F region. So there's only 2 at night and 4 during the day. Now, if you think about it, if we didn't have an ionosphere, all we'd have is line of sight propagation and ground wave propagation, and that it'd still be a hobby, I guess, but it wouldn't be as exciting as it is when we have ionospheric propagation. A little history. Guglielmo Marconi heard a signal from the UK, United Kingdom, in December 1901, and that really started everything off. 2 guys, Arthur Kennelly from the US and Oliver Heaviside from the UK, they theorized a conducting layer as what was responsible for Marconi hearing the signal from the UK. And then Sir Edward Appleton, he proved their theory by sending signals up and receiving them at another location. Now, what they called that conducting region was E for electric. So that's how the E region got its name. And a layer higher, well, that follows that it'd be the F region. A layer lower, okay, that'd be the D region. So now you know where those names came from. And they all started with the conducting layer named the E region for electric. Here's some general characteristics. The F2 region, it's about 150 to 400 kilometers. It's the highest in altitude, and that gives the longest hops. If you think about the Earth and the ionosphere in spherical coordinates, you know, it's not planar. It's not two flat planes. It's a spherical model. The higher the altitude, the longer the hop. Now, the highest electron densities also fall in the F2 region, and that's best for the higher HF bands in 6 meters, 15, 12, 10, and 6. The E region's from 90 to 150 kilometers. Because it's lower, it gives shorter hops, and it can even block signals from getting to the F region where the longer hops take place. And at night, it's reduced to a very low density, and for all intents and purposes, it's out of the picture at night. The D region, 60 to 90 kilometers. And the only thing we can say about it is it's generally a detriment due to ionospheric absorption, which is a loss mechanism. And what it does is drastically reduces signal strength, especially on the lower bands. On the right, there's a brief sketch of the ionosphere. You can see it's not really correct to talk about layers. It's better to talk about regions because it is a continuous electron density profile versus height. Of course, the thick black, the solid black on the right is daytime. You can see it's very strong. And at night, you can see the F2 region still there, and there's still an E region there also. But essentially, the D region goes away, and the F1 also goes away. Now, R equals 200. That's a pretty big solar maximum, and that's what makes the F2 region very good for the higher bands. And at R equals 0, that's solar minimum. And things get kind of sparse. We don't have much propagation on 15, 12, 10, and 6 meters via the F2 region at solar minimum. So how do we measure the ionosphere? Well, we use basically HF radars looking straight up. They're called ionosons. What they do is sweep pulses from about 2 megahertz to 20 megahertz. Some of them only go up to about 15 megahertz. What they do is measure the time of flight for a return pulse and also the highest frequency return to Earth. Now, from those measurements, we can build a worldwide model of the ionosphere for propagation predictions. Now, of course, the model is dependent on where we are in a solar cycle, how big is the solar cycle, the location we're at on Earth, and the month and the time of day. So there's lots of variables that determine what the ionosphere is looking like at any given time. Solar cycles. I threw in this plot of all 24 previous solar cycles. One thing you should recognize is that solar cycles are not constant. They can vary in their magnitude, and it's pretty obvious to see that there is a cyclic nature, at least for the recorded data. That cycle 1 there started in 1749. No, I wasn't around for that one, but sometimes I feel like it, that's for sure. And you can see we've had 3 periods of bigger solar cycles and 2 periods of smaller solar cycles. And then there's cycle 24 way on the right there. That was, it kind of looks like it ushered us into a third period of small solar cycles. It's going to take probably another cycle or two to determine if we are in a smaller period of smaller solar cycles. So what is a solar cycle? It's also known as a sunspot cycle. It's the time period from a very low number of sunspots on the sun, which is solar minimum, through a maximum number of sunspots, solar maximum, and then back down to a very low number of sunspots. That's the A to B to C plot on the right there. And you can see solar maximum is at the B position where the sunspot, we got lots of sunspots. On the bottom, there are the two solar minimum periods between the previous cycle and the next cycle. And that's when we have few sunspots. The solar cycle is approximately 11 years. We've had shorter ones, 9, 10 years. We've had longer ones, 12, 13, 14 years. And on average, the rise time from A to B is about 4 years. And that puts the descent time at about 7 years. So that's just a general picture of solar cycles. So from that, we can determine what the bands will do as we move through a solar cycle. For 15, 12, 10, and 6, the more sunspots we have, the more ionization. What is ionization? What that is the electromagnetic radiation from the sun stripping an electron off a atomic or a molecular constituent. And when we have more ionization, the higher frequencies propagate, and they give us the best propagation on those higher bands. And that's at solar maximum there. That's about where we are right now with cycle 25. Now for 160, 80, 60, and 40 are low bands, and also 160 at medium frequencies, MF. The less sunspots, the less absorption in the D region. That's good. There's less loss. And there are less disturbances to propagation from space weather. So that's when our lower bands are best during the two solar minimum periods there, A and C. Now, that leaves those middle bands, 30, 20, 17. They're generally good throughout a solar cycle. And I grew up hearing people say that if you could only put up one antenna, put up a 20-meter antenna, because that'll work for you throughout a solar cycle. Of course, 20 will be better at solar max, but it's still pretty darn good at solar minimum. And that also goes for 30 and 17 meters. Okay, some fundamentals of propagation. Talk about the rays that your antenna emits. They're not exactly rays. What an antenna does, it spews out lots of radiation at various elevation angles, and of course azimuth angles. But we're going to talk about elevation angles here. Okay, here's a transmitting antenna way on the left there, and suppose it sends up a ray that's straight up. Well, it could be returned to Earth if it's a low enough frequency, or generally it's going to go through the ionosphere because there's just not enough ionization to bend the ray back to Earth. When you think about it, if you send a ray straight up, it has to turn 180 degrees to get back down to Earth. So that requires a lot of bending. Next, there's rays 2 through 15, quite a few of them. As the elevation angle decreases, the ray doesn't have to bend as much. And what happens is the lower the angle, the more the distance. You can see that ray 2 goes up and comes down. That is defined as the skywave skip distance from the transmitter to when the first ray returns to the Earth. Now, the skip distance can be covered somewhat with a ground wave, but usually you can avoid that by going on 160 meters, and that usually covers the skip distance very well. But you can see the lower the elevation angle, the farther the distance. Now, also as the elevation angle decreases, the frequency that can be refracted or bent back to Earth increases. So that's why low elevation angles are critical in the higher HF bands. They don't have to bend as much, get bent as much from the ionosphere, and they go farther distances. So what does it take to make a QSO? Well, there's two things really. There must be enough ionization to bend or refract the signal back to Earth. And of course, as I mentioned before, the amount of ionization depends on our location, where we are in a solar cycle, the month, and the time of day. Now, also the loss must be low enough to hear it with our ears or detect it with a digital mode. This one, we can control some of the parameters. We can increase transmit power. We can use higher gain antennas, better receivers with better sensitivity. And we can pretty much resolve man-made noise if you work enough at it, and also use directional antennas to help reduce the signal to noise ratio. In other words, don't bring in as much noise as normally if you used an omnidirectional antenna. Now, there's some parameters we can't touch there in the loss bucket. We can't control ionospheric absorption in the D region. One of the big reasons why signals can be S9 over S9 on 10 meters is ionospheric absorption is very small on 10 meters, but when you get down to 160 meters, it's very high, and that's why much of the time 160 meter signals are kind of around your noise level. There's also free space path loss. That's the spreading of the wave as it moves away from the transmitter. And also, if there are any ground reflections in a multi-hop path, you'll get some loss from the ground reflections. So, in order to make a QSO, there's got to be enough ionization, and the loss must be low enough. And that all depends on what band you're on. So there are lots of modes at HF. I don't know if I've listed them all, but I tried to think of them. There's single hop, in other words, like from Ozaki to California. That could be a single hop. It could be a multi-hop, depending on the frequency. There's sporadic in the summer. We'll talk about that later. Trans-equatorial propagation to South America on 10 and 6 meters. There's short path and long path. Two ways to get to a target. We'll talk about that later. NVIS, near vertical incident skywave propagation. What you need to do for in-state QSOs is use the lower frequencies, 80 meters. That's why most of the traffic nets are on 80 meters. That's because most of the time the ionosphere can refract high elevation angle signals, which are needed for close-in distances. In fact, I was on the Indiana CW traffic net tonight, and we're on 80 meters CW. And if we're at solar minimum during a winter month, we sometimes have to go to 160 because the ionosphere isn't even good enough to refract 80 meters, 3.5 megahertz. There's ground wave propagation. There's gray line and sunrise sunset enhancements. I'll talk about that later. And there's also skewed paths. What's a skewed path? Well, normally if you if you're going to try and talk to someone in California, you'd point kind of a little bit southwest of west, and sometimes you can point to a different direction and work California. That doesn't happen a lot, but they're out there, and if you're aware of it, and if you have a directional antenna, it's good to take a look, see if the signal peaks on a different azimuth. I think the most prevalent modes are single hop and multi-hop, and that's a little sketch of them there on the right. And it can be from the E region, the F region. And there's a 2-hop path with the ground reflection, which can introduce more loss. And sporadic E is, I just added some more details. It's great for 6 and 10 meters because the maximum usable frequency that can be bent back to Earth either via refraction or reflection can take place. It's not too highly dependent on a solar cycle, but I do have to mention that the past year things weren't that good. We don't fully understand what makes sporadic E good in the summer. There's a lot of stuff still going on that we just don't understand. But right now, sporadic E is best during the summer months in the late morning and early evenings in December. We'll talk about that a little bit later too. So when are the bands open? Well, the lower bands, 160, 80, 60, and 40 are best at night during the fall and winter months around solar minimum. Solar minimum gives us the least absorption in the D region, so that's good for the low bands. And also the winter months, generally the thunderstorms are less invasive. So that means the QRN is lower. So that's when the lower bands are best at night during the fall and winter around solar minimum. Like I said before, the middle bands, they're generally okay day and night over a solar cycle. There is some variation, but you can make QSOs on those 3 bands, solar min or solar max. The higher bands, 15, 12, 10, and 6 meters are best during the day in the fall and winter months around solar maximum. Okay, solar maximum is when the amount of ionization is highest. And these higher bands generally follow the sun. In other words, if you have a directional antenna, in the mornings you'll be pointed northeast through southeast. In the afternoon, you'll be pointed southeast through southwest. And in the evening, you'll be pointed southwest through northwest. So propagation follows the sun. The digital modes have an advantage over sideband and CW. When they decode the waveform, they use a very narrow filter that is commensurate with the bandwidth of the mode, the digital mode, and that reduces the noise significantly, so they have a much higher signal to noise ratio. In our last solar minimum, will go down in history as the first solar minimum with very high activity on the higher bands. Normally at solar minimum, 15, 12, 10 meters, and even 6 meters aren't very useful. All you hear is noise. But FTH sure changed that. It came into the amateur radio world in mid-2017, and it has taken off. In fact, it dominates of all the modes we use in amateur radio. It dominates all of them. FT8 is, there are more QSOs via FT8 than sideband CW RIDI combined and some of the other digital modes. So we've evolved into a digital hobby, but there's a lot of us that still like the legacy modes though. Also, I'll mention that the equatorial ionosphere is very robust. It's where the highest electron densities are. And as you move toward the poles, the ionization decreases. And what that brings up is those at farther south QTH than us can have better propagation. I see lots of times where the guys down in the southern states are working stuff and I can't hear a thing. And I'm sure you've can witness that on the HF bands, especially 15 or 20, 15, 12, and 10. It's kind of aggravating, and the only thing you can do is move farther south if you want to. Okay, here's some general observations about sporadic E. On the right is a plot of the probabilities of a 6-meter opening versus month and local time. It's 2 years worth 2 years worth of data, 1957 and 1958. There's still, although that data is old, it's still good by recent measurements of when 6-meter propagation is best. And I've highlighted the maximum probabilities in the green. And you can see, for example, in 1957, in the May, June, July timeframe, late morning is the highest probabilities, and early evening is also the highest probability. That's 50% of the days, so that's pretty darn good. You can see the December, it's only in the early evening, and then 58 kind of mirrors what happened in 57. So just remember that. So don't ever forget about sporadic E in the summer and December. In the summer and in December, there's no guarantee it'll be good, but always take a look. And summer sporadic E could certainly help your field day operation, especially on 10 meters and 6 meters. We just got to hope it happens. General observations, the F2 region summer slump. Now, each year, the F2 region goes through a slump in the summer. In other words, the electron density in the summer decreases. That's because there's a change in the composition of the atmosphere. And here's a plot of the maximum usable frequency at 1500 UTC from K9LA to England at 3 different levels of a solar cycle. And you can see that the best time for that path is in the fall and winter months. In the summer, the MUF drops below 12 meters, and even sometimes it could be less than 15 meters. So again, hope for sporadic E in the summer for field day. And that also applies if you're an HF contester for the IARU contest in July. If sporadic E happens, that'll make that a really good contest. If no sporadic E, 10 meters will be kind of sparse. Okay, general observations, the F2 region night and day. Now in the northern hemisphere, the daytime fall winter F2 region ionization is greater than the daytime summer F2 region ionization. You can see that on the right of that XL plot. Blue is the winter day, orange is the summer day. You can see the ionization is higher in the winter months than the summer months. Now, going the other way, in our northern hemisphere, the nighttime summer F2 region is greater ionization is greater than nighttime winter F2 region ionization. You can see that on the left side of that plot. So when we're out of field day this year, check for 20 and 15 meters at night because the MUF, the amount of ionization could be high enough that those bands will still be open. They might not be enough to help 10, and that's where the early evening sporadic E could help 10 meters during field day. Another thing to observe, if there's a spike in the K index, we'll talk about the K index a little bit later, but if there's a K index spike, if there's a moderate spike for a short time, check for higher frequency enhancements on middle and low latitude paths. In other words, paths that stay at middle and low latitudes, pretty much like from us to VKZL is a good example. And there are two examples when that happened. The one on the left is from the Eglin Air Force Base down in Florida. And it's for August 4th, 5th, and 6th of 2011. You can see the blue is the either megahertz for the MUF, the maximum usable frequency, assuming a 3,000 kilometer path at which Eglin is the midpoint. You can see the MUF is around 20 megahertz, but then the K index spiked up to 5 and 6 late on August 5th, and look what happened to the MUF. It went up all the way to 35 megahertz. So if you caught that spike and then went on the 10 meters, you probably had some contacts. The other example is from Wallops Island, Virginia. In March 2024, you can see there's a single spike in the K index all the way up to 7. And you can see that the MUF over the Wallops Island ionosonde increased from maybe 40 up to 45 megahertz. That's getting temptingly close to 6 meters. So that could have made some exciting times for the 6 meter ops. So just keep an eye on there if you're active on the higher HF bands. It includes 10 meters too for techs. Short path and long path. So one possible path is from southeast Wisconsin, where Ozaki is, to Japan. And that's what I've shown here. The red line is short path. The black line is long path. This comes from the W6EL prop mapping program. It's kind of nice. It shows the terminator, you know, the division between night and day. And also right over Africa, you can see that star. That's the overhead sun. So you can see it was just past sunrise in southeast Wisconsin. And the path I chose is to Japan. That's where and I should have marked it, that's where the red and black come together on the left side. That's a 6,300 mile path. It's best in the fall and winter. Long path to Japan. It's about 18,500 miles. It's best in the summer. You can see what the headings are. For short path in the fall and winter in the evening, you're pointed towards the northwest. For long path in the mornings, you'll be pointing to the southeast. And you can see your long path goes over the Caribbean, South America, almost touches Antarctica, comes up through pretty close to VK6, the Western Australia, also through the Philippines and into Japan. This long path is best in the summer, where that's where we are right now. So if you want to try some long path QSOs to Japan, during May and June and July. Take a look. Here's some data from K2ARO on the East Coast to JA Longpath. It's his data from 1979 to 1993, and it shows the number of days in each month that had JA QSOs via the Longpath, and you can see it kind of peaks in the summer months. So right now is a good time if you want to have some fun, is get on 10 meters and point your antenna, if you have a directional antenna, to the southeast and see what happens. Now, there are also short paths and long paths. They can both be open at the same time, and that can make copy very tough because the time difference is about 1/7 of a second. And I've had conditions, I've heard conditions when you just can't tell what the person's sending because they're so similar in amplitude, and the time difference isn't that much, and it can make a mess of things. But there are two ways to get to a target, via short path and a long path, and which one is best depends on is there enough ionization, and is the loss low enough? Back to the two basics for what's making a QSO. Okay, gray line and sunrise sunset enhancements. I think sometimes those two get confused. They're two different mechanisms, we believe. On the left is St. Louis to VQ9 out in the Indian Ocean. And that is a gray line path because the long path, which is the black, well, also the short path, they align with the terminator, or they're very near to the terminator. And there usually can be a very short duration enhancement at, like, for example, at the St. Louis sunrise time. And many people have worked some pretty good stuff on 160 and 80 meters that way. On the right is a different path from St. Louis to Italy on the short path. When the path is approximately perpendicular to the terminator on the east end, there can be a longer duration enhancement at the sunrise on the east end of the path. One of the best ones I heard was to the de-expedition in Sudan many years ago, and at their sunrise, it was pretty much like that path there. It went a little bit to the north, then was kind of perpendicular to the terminator. They came out of the noise for about 20 minutes, and that was just spectacular. I wish I would have recorded that, but oh well, I didn't. So there are two things, gray line and sunrise, sunset. That's a good thing to know, is the sunrises and sunsets at your location and your target location, and see if something may fit here to help you out. Space weather. What is space weather? Well, it's everything that isn't terrestrial weather, I guess. The three disturbances to propagation are geomagnetic storms. That's when the K index becomes elevated, and we can have a coronal mass ejection. A CME can do that, or a coronal hole can do that. And what a geomagnetic storm, it can decrease the F2 region ionization day and night for many days. So it's the worst of those three disturbances that are the first three bullets. Solar radiation storm. What can happen is, from a flare and a CME, protons in the solar atmosphere can be accelerated to relativistic speeds, and they funnel into the polar cap. And what they can do is increase the absorption in the polar caps, and that causes an adverse impact to over the pole pass, like from Ozaki into deep Russia, India, etc. And that can happen for a day or two. So it's not as may not be as long as a geomagnetic storm, but it's up there. But most of the time, our paths aren't over the poles. That helps. And the third disturbance is a radio blackout. That's from the X-ray radiation from a big flare. It can cause increased ionization in the D region on the daylight side of the Earth, and a band can go away. You can, whoa, did my antenna fall down? Did I take the coax off the rig? All that kind of stuff. And the lower bands are affected the most. That hour time frame, that's pretty much for mostly for like a 20 meter. On 10 meters, it's a little bit shorter. On the lower bands, it's even longer. So, but it's not as long as a day or two or many days. Now, can we use space weather data to predict propagation and predict storms? Somewhat. But remember, we're trying to simplify some very complicated processes in the atmosphere and the ionosphere into simple statements about HF propagation. We know a lot about the ionosphere, but we don't know everything about its variability yet. And that's why I said we can somewhat determine what's going on. One of the ones that I like to look at is the N0NBH banner. It's available at qrz.com. It's available some other places too. And there's a lot of colorful data on there. And what I think are the two parameters that are important to look at are SFI, that's the solar flux index. And you can see on the day I pulled that way back in 2023, the solar flux is 159, not bad. And the solar flux can indicate which of the higher bands may be open. Of course, you got to go see if the K index is too high, which may say the band isn't open, even though there's enough solar flux in there. And there's a general correlation between that SFI, solar flux indicator, or solar flux index, SN, which is sunspot number, EUV, extreme ultraviolet, and the MUF US boulder. They're generally both high or both medium or both low. So there's a correlation, and that's why I think it's easiest just to go look at the SFI, the solar flux. Of course, it's on WWV at 18 minutes past the hour, and spaceweather.com and a whole bunch of other places. The other parameter that I think you should keep an eye on is the K index. Okay, it tells us how disturbed the Earth's magnetic field is. And the more disturbed the magnetic field, the more screwed up the F2 region could be. There's also a general correlation between the K index, the A index, the Z index of the sun, the sun's magnetic field, and also SW, which is the solar wind. If the K index is high, generally the A index was high. The B sub Z is high negative, and the solar wind is high. You can see on that day, the K index was 6. So the B sub Z, that's the component of the sun's magnetic field that is perpendicular to the ecliptic. The ecliptic is the plane in which the planets go around the sun. And just think something that's perpendicular to the ecliptic is kind of like what our magnetic field is, north and south. So it's a -6, so it's getting up there. It'll be interesting to watch. The solar wind was about 800 kilometers per second. Normally it's about 400 on a quiet day, so that's getting up there. So what we desire from all those two parameters, The daily solar flux can go from 65 at solar minimum all the way to 350 at a big solar max. The daily data is very spiky. If you average a month's worth of data and look at the monthly averages or monthly means, it's better. There's still some spikiness. So further averaging gives us smooth values. And of course, if you plot the daily solar flux, it's going to be very spiky. If you plot the smooth solar flux, very heavily average, it's going to be a very smooth plot. So for 15 meters, we desire a solar flux greater than 85 for a long time, not just a couple days, for a long time. For 10 meters, we desire greater than 100 for a long time. Now, at solar flux is 65, there's still enough extreme ultraviolet for 17 meters in the lower frequencies. So that's why I said the middle bands are pretty good, because even if we get minimum solar flux, which also would correspond to 0 sunspots, we still can have 17-meter propagation and propagation on the lower bands too. Now, right now, in cycle 25, the smooth solar flux is almost 200. That's well above what's needed for 10 meters, and that's why 10 meters was really good in the fall and winter. Remember, we're going into the F2 region summer slump, so we're going to be seeing less propagation on 10 meters, 12 meters, and probably 15 meters. But it's going to come back in the fall and winter. The K index, that's a 3-hour index. It's logarithmic from 0 to 9. 0 is the Earth's magnetic field is quiet. 9 says the Earth's magnetic field is disturbed, which again could mean the F2 region is screwed up and things aren't doing too good. Generally, we desire K index less than or equal to 3, and that's kind of pretty much quiet conditions. Of course, if you're a VHF aurora type guy, you'd like to see the K index up around 6, 7, 8, maybe even 9. Now, the daily A index is a linear measurement from 0 to 400. If 0 is quiet, 400 is the Earth's magnetic field is disturbed. And the A index is an average of the 8 3-hour K indices. So it's a daily index, whereas the K index is a 3-hour index. It's more real time. So I think the big takeaway is, although the solar flux parameter may indicate there's enough ionization, the K index may say the band is not good. So that's a good hint. So what can you do about that? Well, you can go look at some real-time QSO data. This is dxmaps.com, and I looked at that yesterday at about 9 o'clock your time. You can select what kind of view you want. I selected a world view, and I selected 10 meters, and you can see what's going on. There are people spotting their QSOs, and you can see what's going on. There's lots of contacts from the East Coast into Europe, and even looks like North Africa. It looks like there's some propagation to the southeast into a deep Argentina, which is probably trans-equatorial propagation. And there's even looks like somehow a QSO happened between on 10 meters between California and looks like kind of Eastern Europe. So it's interesting to look and see how that happened, but it was a pretty good day, it looks like. You can see England was also working into deep South Africa, which is trans-equatorial propagation. There's similar info like this at prop.kc2g, at PSK Reporter, WhisperNet. There's the Reverse Beacon Network, and the Northern California DX Foundation beacon system on 2017, 15, 12, and 10 meters. There's lots of ways to see what really is going on the bands, so we can get a general idea from the K index and the solar flux index, but this is a real easy way to understand if there's something going on the band, and you should turn your radio on. Cycle 25. Well, there's a picture of the sun at solar minimum on the lower right, few or no sunspots, and then at solar maximum, up in the upper left, there's a lot of black dots there. Those are sunspots. And things can get pretty interesting around, they were around the peak of cycle 19, which is the biggest in recorded history. So here's what cycle 25 is doing. I also have 4 other solar cycles on there just to show where cycle 25 fits into the grand scheme of things. The solar cycle 25 progress is the thick red line. We have almost 5 years worth of data now. The green plot was cycle 24. The one we just came out of, it was cycle 24 was the smallest in our lifetimes and the 4th smallest in recorded history. So it was a small one. And like I said before, it may have ushered us into a 3rd period of small solar cycles. We'll see what happens. The orange plot is cycle 23. If you average all 24 solar cycles, cycle 23 was pretty much an average cycle. You can see cycle 25 is getting darn close to cycle 23. So have to see what happens in the next 6 months or so. The blue is cycle 21. It was a moderately big cycle. And then there's cycle 19, the biggest in recorded, the largest in recorded history. So cycle 25 may go down as an average cycle. We'll just have to wait to see what happens. It did surpass cycle 24. Yay. We had some pretty good propagation during cycle 24. So that means cycle 25 is going to be better. And in fact, it has been. I don't think cycle 25 is going to get much higher. There have not been a lot of sunspots in the month of May so far. So I don't know if that signifies it's going to start its descent, or it's just, at solar maximum, things could go up and down. So we'll just have to wait and see what happens. Here's some references for propagation: ARRL handbook and the ARRL antenna book. ARRL's kind of new book, From Here to There, Radio Wave Propagation. NM7M, he's a silent key, but he wrote a Little Pistol's Guide to HF Propagation. It's a very easy read. It's out of print, but it's available on my website, which was listed on the introductory slide. It's a 15 megabyte download. That's probably not much of a problem nowadays. And also, in 2021, there was an update to the CQ Shortwave Propagation Handbook. It was the 4th edition. Unfortunately, it's out of print and CQ is gone. So that was a good book too. Oh well, things like that happen, I guess. So here's a summary. Get on the air and operate. Experience is a great way to gain knowledge. So go make QSOs and contests. Chase worked all states. Chase your DXCC. Chase the CQ worked all zones. Even though CQ is gone, N4 BAA takes care of the worked all zone award. So that's still going strong. And especially have fun on 15, 12, and 10, especially now that, cycle 25 is at solar maximum. And use the digital modes, especially FT8, on those higher bands, if you are power challenged and antenna challenged. If you live in an HOA, you might be able to string something up. I know a lot of guys do. They've managed to get on in an HOA without bringing any trouble to them. So mostly the FT8 modes, the Whisper. Oh man, I think Whisper normally runs at 100 milliwatts or 200 milliwatts or so, and it can be heard worldwide on the right bands at the right times. So take advantage of the digital modes. And we're probably moving into a digital ham radio more and more, thanks to Joe Taylor and his colleagues when they introduced all those weak signal modes. So, Bill, that's all I had. You have the presentation as a PDF. You can do whatever you want with it. I didn't catch any typos as I was going through here now. So
I think it'll be made available, or most of our programs are eventually make their way to YouTube.
Okay.
Under our banner.
Okay. So if there are any questions, I can try and answer them.
If you're on Zoom, don't forget to unmute before you have a question. And Carl, I do have one. I'll kick it off here. W9MXQ. Is propagation generally a mirror image in the Southern Hemisphere? You touched on the Southern Hemisphere in your presentation, but I don't know.
Yeah, it's summer, when it's winter up here, it's summer down there, so their MUFs are going to be lower during the summer. And when it's summer here, well, it's winter down there, and their MUFs are going to be higher during the daytime. So, yeah, there's yep.
Somebody else have a question there?
Yeah, Fred here. Hello, Carl.
Hello, Fred.
W9KEY.
Yep.
I'm curious, what happened to the MUF Boulder numbers? They haven't been shown on the reports I've seen for quite a while.
Yep. Well, that's Boulder isn't the only one. There are a lot of ionosons that aren't being reported. There's some models that use ionoson data, and of course, they're not available. And it seems to be that we're headed more towards why should the public get all that information for free? I don't know what else to say. It's a conscious decision to not report it publicly. That's Boulder. There's some other ones. Europe still has a good representation of ionoson data. They haven't done whatever we're doing, and that's good. But right now, the Eglin ionoson in Florida, the Idaho National Labs in Idaho Falls, Idaho is still running. I think the Vandenberg ionoson is still reporting. And that's about it. 3 ionosons in the whole United States, or the continental United States.
So they're still operating. They're simply not releasing the data. Is that right?
They're not reporting it to the places where other people use it to put together graphs and all that kind of stuff. Yeah. Yeah. It's frustrating, Fred.
Do we have any questions from the room? Going once, twice?
Peter.
Carl, thank you.
Oh, I have one question there. Peter here, W0NG.
Mm-hmm.
Are you familiar with Schumann resonances and how that affects the ionosphere?
Not enough to speak on it.
Okay.
I'm not
well, the Earth seems to have more Schumann resonance components than a couple years ago. And that could be, if you watch the YouTube channel, Stefan Burns, he talks about the Schumann resonance. And anyways, whatever, it's worth looking into.
Yeah, there's a lot of stuff we don't know yet, and you know that brings up it sure looks like sporadic E where it occurs has moved in location. And the East, well, the Midwest, it just isn't in the right place now where it used to be. So what's causing all that? The terrestrial weather or something else, or the change in, the Earth's magnetic field is weakening, and especially the North magnetic pole is moving rather rapidly towards, I think, Siberia. So there's a lot of stuff, and yeah, I've read about Schumann resonances, but I really haven't paid enough attention to just, tie it to anything.
Fred here again. I just wanted to make a comment. Carl contributed, I believe, to this book, which ARRL is now putting out from it's Here to There Radio Wave Propagation, and it's fabulous. It's just a really nice summary. I can read about 3 pages and then my brain overloads and I have to set it down and wait a couple hours to pick it up again. But I'm about halfway through, and it's great. I don't remember where I got it. I think maybe by renewing my ARRL membership.
Yeah, I think they offer you can either have this book or that book or some other book, and maybe that was where it came from.
But if you're coming to HRO Superfest this year, I want you to sign my copy.
Oh, well,
Great.
I'm not the director, so I may not be there, but that's N9BA and W9HT's job now.
I know, but I thought maybe you'd just come for old time's sake.
Oh, I could. Yeah, I enjoyed all the ones, even when it was what was it before HRO?
AES,
AES.
Amateur Electronic Supply.
Yeah. Yep.
Carl, could you talk a little bit about reciprocal propagation? I was told when I became a ham that a lot of times signals go both directions equally well. I found that to often not be the case.
That's right. Yep. Yeah, that's still an open subject. I've looked at several examples and don't see why it happened. I mean, I've had 2 very good observations in contests, and there's still something we're missing. The obvious issues are one guy's running more power than the other. One guy has more noise than the other, and stuff like that. But generally, you can throw that stuff out, and there's something else going on. It may have something to do with polarization, which we as hams don't really pay enough attention to. So, don't know.
It's
It
especially, you can really see it in FT8, where you can look at incoming signals and where they're coming from. You don't have to look up a call sign. And those signals are sometimes incredibly strong, and you try to reply to them, and you look on things like PSK Reporter to see where my signal is being heard, and it's not coming down anywhere near where the person is that I'm listening to. And
well, see, you got to remember, you have no idea what power they're running, and what they report is signal to noise ratio, and you have no idea about the noise that they have either. So, yeah. But I'm sure there are some that make you wonder what the heck's going on. Yep.
Okay. Carl, excellent presentation, excellent questions. If you would, Carl, please stop sharing your screen.
Okay.
And you are more than welcome to hang on, stay here for the meeting, and then maybe answer additional questions or join a discussion after our meeting.
No, I think I'm going to cut out. It's 10 o'clock and we got to take care of some cats and all that.
Very good. Very good. Well, thank you. Ton digest. And we really appreciate your
Okay.
availability tonight.
Thank you, Gina.
Thank you, Carl.
Bye-bye.
Glad you're-
We'll see you.